Hello, everyone. Welcome to the second part of our series titled Machine Learning from a Simple Line to Generative AI. In the first part, we have covered the foundation and the concepts of machine learning and neural networks. And in particular, we have stressed on the concept of a loss function. And we have also alluded to how we represent a word as a vector. In this second part, we will focus on generative AI and its techniques and concepts. We will be talking about embeddings, positional encodings, and transformers. In this part of the series, Ali Wadi will be joining us and enriching our presentations. Ali Wadi, feel free to introduce yourself. The mic is yours.
Thank you, Khalid. Hello, everyone. I'm Ali Alwadi. I'm still a PhD candidate in University of Canberra in Australia. I'm also a principal cloud engineer in a well-respected company here in Queensland, Australia. Uh, I'm still doing my PhD in machine learning as well. I do have a lot of experience in machine learning in general, and we're trying to apply that to the medical sector in bone fracture detection and localization as well. My main research interests are machine learning and artificial intelligence, in addition to many other things as well, like e-health, Internet of Things, and many others. I do have lots of experience in serverless computing and also cloud computing as well. And lots of my experience cross a lot with machine learning. And I think that's enough introduction about myself, Khalid. So I'll give you the mic back.
Thank you, Ali Wadi, for the nice introduction about myself. I am a PhD. I have a PhD from State University of New York at Binghamton, and I have long expertise in software engineering, computer architecture, and performance analysis. My research included energy optimization and modeling in Java virtual machines. That being said, let's start our presentation there. Let's start with the outline of today's presentation and what we are going to learn. At first, we will revisit and reinforce some of the concepts that we've learned, including the loss function. And after that, we will talk about multi-output machine learning models, where a model can predict more than one value instead of just one value. And then after that, we will revisit the gradient descent algorithm, and we will talk about classification tasks because word-to-vector algorithms are really just classification tasks, or they are treated as classification tasks. And then we will meet our very friendly log function here, and it's going to be very friendly. It's not going to bite, I promise you. If it did, you can sue our presentation series. And then after we introduce the log function, we will start talking about the word-to-vector algorithms, and then we will see how we feed sentences into the word to vector algorithms, because once we feed it sentences from a large corpus text, this is how it learns to represent a word as a vector. And after we develop this concept, we will introduce the notion or the principle of a hot vector. And this is where we will see the mathematics of how a word is represented as a linear algebra vector. And this takes us to the embeddings matrix, where each column or each vector in this matrix represent a word. And this is the ultimate goal of our presentation. So we're ready to jump into the next part of the presentation. Now, let's talk about the loss function. Previously, we've mentioned that when we have a machine learning model that makes a prediction, we need to quantify the difference between the actual value and the predicted value. So we need a function that quantifies this difference. And this is the loss function. We've seen before that the squared difference is this loss function, which takes the prediction minus the actual and squares that. And when we apply the data set to our loss function, we get a large function in terms of W0, W1, to W4. For example, each weight could represent the number of rooms, the number of bathrooms, if we are trying to predict the price of a house. And the machine learning process is finding a minimum point on this loss function. So at the end, our model is just a point in a global loss function. Previously, we have the examples we have provided. The machine learning models predict only one value. For example, the price of a house based on some attributes of the house, like the number of rooms or the number of bathrooms. In this presentation, we will talk about multi-output models where the model predicts more than one value. And this is really no different than predicting a single value. We apply the loss function to each node separately, and the loss function is just the sum of the loss of each output node. So it's basically and mathematically the same. We just want to present this for simplicity because we have not talked about this in the previous series, and it's the time now to talk about it and introduce it. So we need to mention the concept of we need to revisit the gradient descent algorithm, and the gradient descent algorithm is where we minimize our loss function. The gradient descent that we have introduced in the previous part of the presentation is where we feed all of our data to the loss function at once, and we have a large function in terms of W0 to Wn, which represents the features of our data. Now, feeding all the data at once is called batch gradient descent, and we update the weights. Each weight is updated in a each weight is updated by a value proportional to the gradient of that weight, and the gradient is proportional to the amount of loss. And after we finish updating, we evaluate our model. Did it predict well or no? For example, across all the data points, we sum for each data point. We take the prediction minus actual, we square that, and maybe take an average, and this tells us how well we are doing. There is
So
another,
just to
yes,
be clear, so
yes,
you evaluate your accuracy of your model based on the sum of the prediction minus the actual squared.
exactly, yes, exactly. So
So
after we
that's
update
how
the
you
weight,
minimize your error.
yes, yes. So after we update the weights by gradient descent, we need to know how well we are doing. How do we know? We need to take the prediction minus actual for each data point, square that, and take an average. This will tell us how we predict, how well we are doing. Does that answer your question?
Yeah, yes, absolutely.
And you see here, repeat or stop. After each point, we do, after each point, after each update, we after we double check, are we doing good or not? We repeat the same loop until we reach an
Yeah,
acceptable performance or acceptable accuracy.
yeah. So the
Yeah, that's
model
it.
decides to stop or repeat based on that value that you just extracted from the prediction minus actual.
Exactly. Yes. Exactly.
Yeah,
This is our criterion. Yes. Yes. For example, the price of the house might be 10,000, and then you're predicting 8,000. Maybe that's acceptable. Maybe some might not see that as acceptable. So the stochastic gradient descent, instead of feeding all the data points to the loss function, we only feed one point to the loss function. And this point, we apply it to the loss function, and it will give us a loss function in terms of W0, W1, and W4 again, the attributes of our data set. And we pick and this, after we feed this point, it will update the weights. And also we pick another point, we feed it to the loss function. It will give us another loss function in terms of the weights. That loss function related to that point is different from this loss function. It's just the coefficients. And each point updates the weights. When it updates the weight, when it updates the weights, it will move our model in the global loss function closer to the minimum point. That is the hope. When we finish iterating over all the data points, this is what we call an epoch. So each point updates the weights, and then after we finish updating the weights from all the instances, we evaluate our model again. This is the question, Ali, that you have asked in the previous slide. And then we decide, shall we stop or shall we repeat? So the takeaway of this presentation, or sorry, from this slide, is that each point will have its own loss function that's a little bit different than the other node, but when it updates the weights, it will move our model closer to the minimum point in the global loss function. And you can imagine that the global loss function is the function that results when you feed all the points together at once. Here, another variation is called the mini batch gradient descent. And instead of feeding one point at a time, we feed a group of points. It's like dividing our data set into multiple groups. For example, a group of 3 or a group of 10, and we feed these 10 points together, and then each group will give us a loss function. And again, the weights will be updated according to the gradients. And once we update the weights, it will move our model closer to the minimum point in the global loss function. So there is like two concepts. I want to emphasize the global loss function and how we apply the data to the loss function. Maybe a point or a sample by sample, a group of samples or a group of instances or all the instances at once. So this is just a recap of the gradient descent algorithm. Dr. Ali Wadi, do you have any questions at this point or any additions, or shall we
No
proceed?
questions. You explained it really well, I have to say.
Okay,
Thank you.
thank you for that. Let's move to the next slide. So machine learning tasks can be regression and can be classification. For classification tasks, we need to predict, is this item a banana? Is it an orange? Is it an apple? Or regression task. Regression tasks, basically, I'm trying to predict the number of ice cream sales based on the temperature. And there is a saying that says, ice cream, you scream, all scream for ice cream. So, in the previous part of the series, we talked only about regression. In this series, we will focus on classification tasks. So, what are the different types of classification tasks? There is a single label and multi-label. Single label means that the instance or the data point applies only to one class. I'm trying to predict customer sentiment. Is the customer satisfied, dissatisfied, very satisfied, or very dissatisfied? There is only one label. The customer cannot be dissatisfied and satisfied at the same time. Multi-label means that more than one category can apply to the data point. For example, I want to market a certain product. What is the best way, or what are the best channels to market this particular item? Is it through email? Is it through SMS? Is it through push notification, or is it both? Or some products, maybe I better send an SMS. Some products, I better send an a push notification or an in-app message. How does the classification tasks translate into the neural network model that we know? For each class or for each label, there's an output node in the neural network, and each node will produce a value between 0 and 1. Because when you're trying to predict the class, it's like saying, what is the probability that this instance belongs to this class or belongs to this category? If you are only predicting a single label, then all of the nodes must be 0, and only, except for one node, it's going to be 1. If you are predicting multiple label prediction, if you're doing multiple label prediction, then each of the output nodes will be between 0 and 1. So
I
that
can
being,
interrupt quickly.
yes, go ahead, Aliwad, please.
So your probability of prediction is more of a, let's say, the your model's confidence that this is the actual object that was predicted. So let's say if I say I'm 60% confident this is a banana, if the model says I'm 60% confident this is a banana, that represents the probability, right?
Exactly, yes, exactly, yes. The model says I am 60% confident that this is a banana. Exactly. That's a much better way to put it.
Okay, that's
Now, yep,
yeah.
now, how does the model actually produces this zero value from 0 to 1. There is something called the sigmoid function. The sigmoid function takes a value and it produces a value between 0 and 1. And here's just a table to show that the less value it receives, or the less signal it receives, the closer the value will be to 0, and the higher value, the closer the value will be to 1. And we have seen that this sigmoid function actually is used in earlier versions of neural networks as an activation function, and then they switched to rectified linear unit, as we have shown in the second presentation of the first part of the series. So this is how neural networks are able to produce a value between 0 and 1. And you can look at it and try different values to get the feel of the function. So this is the activation function of the last layer when we are talking about a classification tasks. Let's meet our friendly log function. The log function basically tells you the power. For example, how you go from 2 to how do you go from 2 to 16? How? Can you tell me how do you need to go from 2 to 16?
Power.
You need power because the log tells you the power. So 2 to the power 4 equals 16. The log of 16 to the base 2 is 4. 2 to the power 4 equals 16. And why do we care about the log function? Because the log function is good at quantifying our prediction accuracy for classification tasks. So let's see an example. So as we have mentioned, in a classification tasks, an instance or a data point can belong to a category or it does not belong to a category. There are two situations. Either this data point it's either a cat or not a cat for one output node, right? If that item is a cat, our prediction should be 100%. If it's not a cat, it should be 0. As simple as that. So assume that this instance or data point is a cat, and we predicted, and our prediction was only 1%, 0.01. The minus log of the probability will give you a high value, 4.61. However, if that point or instance was not a cat, that means we did a good job in predicting, and the loss function will have low value, close to, for example, 0.01. Does that make it clear? Have any questions at this point?
Yeah.
It's clear, right?
Yeah.
Okay. And this is just table, it's for a clarification. We might double check the numbers after the presentation, or we can leave this to the audience to double check the numbers, but this is the idea, right? Let's go to the multi-classification loss. So a neural network can, as we have mentioned, with multi-output neural networks, there could be multiple labels, and one instance can belong to more than one category. And each output node shall predict a probability. For example, in the marketing example we have mentioned earlier, we were trying to predict what is the best channel to market a product, via SMS or via text or by email or by push notification if you have the app. And this is basically just we are formalizing the loss function. It's just a collection, the summation of the loss function for each of the node. So here, if you look at this one, the first example where the label does not apply to the instance, the checkbox is not checked, we take the log of 1 minus our probability, so it gives us the log of 0.6. And which is here, this column here shows our prediction, and this column here shows the actual, if the label applies or not. And if the label applies to the instance, for example, assume this is an SMS, we should market it through SMS, and we predicted only 35%, we take the log of 0.35, and we sum this formula for all of the output nodes, and this is our loss function. So our loss function is just the sum of the error or the loss of each node, and depending on whether the label applies to the data point or not, we either take log of p or the log of 1 minus p. I hope that's clear. Please do ask
Yeah.
any questions if there's anything that's not clear. Shall I proceed to the next?
Yes. Yeah, let's
Okay.
go.
Okay. Now, assume that we have so many labels. Assume we have 40,000 labels. Are you going to go and sum the errors of each of these labels? Does that sound economic, or does that sound...
That's not really practical.
It's not very practical, also perform worse. So there is something called negative sampling, where you only calculate the loss for the nodes where the label applies, and where the label does not apply, you take a random sample. Let's say you take 10% or 5% of those, and that's basically what's called negative sampling. That's it, as basic as that, and we still have the same error function. Let's now move to a simple label classification loss. Basically, there is the difference between multi-label classification loss and single label classification loss. It's the same dir loss function, except that if you look here, the output nodes, their summation must be 1. So each node will not to produce a value, each output node will not to produce a value between 0 and 1. Their collective sum will be 1. And once we do that, we apply the loss function the same way we applied before. The catch is here is that all of the nodes together have to sum to a value equal 1. How does that happen? There is something called a softmax function, and this softmax function takes values and it will convert a value to a probability. Remember, that's a neural network, and a node receives signals from previous nodes and calculates a weighted sum of these signals, and based on the value, the softmax functions will give you a probability. So if you look at this sum here, for example, do you know like the standard way we normalize values, where we calculate the value of an item by the sum? The softmax, why it is called softmax? Because it's kind of isolating the max. You take the power, e to the power each value, multiplied by the sum of e to the powers. So that's why it's called the softmax. If you look here, 10, for example, this is the maximum value, right? 10 over the sum, in this case, it's just 35%, but when we apply the softmax function, it gives you 87%. And why we need a softmax function? Again, because it is a single label classification. So where the label applies, that value or that node must be pushed higher. It must have a higher value so that we can apply the loss, right? And
Okay.
let us proceed. So we are now ready to explain the Word2Vector and how the Word2Vector works. So as we have mentioned, it is very important once we represent an object, a daily life object in mathematics, like a car or a product, we can use the magic of mathematics and the well-established rules of mathematics to draw conclusions, right? And that's the idea behind many machine learning algorithms. So there are two variations of Word2Vector algorithms or Word2Vec algorithms and how they work. Imagine you have a sentence, and this sentence is Word2Vector is fun. And if I give you the word vector, can you predict which word appeared in the same sentence? This is called skipogram. Or there is another way called continuous back of words. If I just give you the context, can you predict that the hidden word is vector? We will get into the details of each, but we're just talking here high level of how they work. Now, how do we feed those? How do we feed these sentences? We do not only feed one sentence and that's it. We feed many sentences. But before we talk about how we feed sentences, let's look at the neural network or the model. We talked about the classification tasks, and here where the classification tasks come into play. in terms of the continuous back of words, we have a neural network, and imagine for a while, imagine for a short while that we can feed direct text to the neural network, and the output here is, let's say we have a dictionary of 40,000 words, right? We will have 40,000 output nodes of coming out of the neural network. So you input where to is fun, and then you should predict only fun in terms of the continuous bag of words. So that's why we treat it as a classification problem. Now, in the skipogram, you feed one word and you are trying to predict four words. So skipogram can be seen as multi-label classification problem. And again, the output layer is the number of words in your dictionary. It could be 50,000. That's why we have mentioned negative sampling, is that you have we have so many output nodes and only four of them or five of them or 10 of them, we have to predict that they are actually in the context, but we have only to sample some negatives. So that's why we have mentioned the negative sampling approach. So how do we feed sentences into the Word2Vector algorithm? We have a corpus of data, and this corpus of data, we start with a sentence, and the amount of words in a sentence is called the context or the window size. And we hide a word or a couple of words if you are using skipogram or continuous back of words, and you feed it to the neural network. And it tries to predict and update the weights accordingly. And then we slide. If you look here, we slide one word, and then we keep sliding until we go through until we go over the whole corpus of text. So we are not far from the magic. Now we will talk about how do we feed the actual words into the neural networks or into the machine learning model. So we mentioned that we cannot feed text directly into the machine learning model, and probably we are approaching the last piece in our puzzle. So we will introduce the concept of a hot vector. And a hot vector, basically, if we have 50,000 words in our vocabulary, that means we will construct a vector basically of 50,000 dimensions, and each word is associated with one dimension. So that means each word is represented by one unique vector where the associated dimension is one, and all the other dimensions are actually set to zero. Similar thing, there's something called the sparse vector, where one vector can represent multiple words. That means I am feeding multiple words into the neural network, and we just turn on the dimensions related to these words. That means we set their values to one. So this is the sparse vector. I have to mention one thing here. We have mentioned that in the previous presentation, but I should emphasize on this, is these are not actually the actual words. These are the text corpus after tokenization. We do tokenize. That means breaking each word into subtokens if we can. And we have discussed a tokenization algorithms in the previous lectures. So what is the last piece in our puzzle? This is the last piece, is that we do not, how do we feed a word into the neural net? We don't feed textual word into the neural network. In fact, we do feed the hot vector into the neural network. So let's refresh the matrix multiplication. Matrix multiplication is basically you multiply a matrix by, and a matrix is just a collection of columns, and you multiply a matrix by a column, and this column determines how you need to sum each column, or that's called a linear combination of the columns. For example, 0 multiplied by C1, 1 multiplied by C2, because this is 1, and then 3 multiplied by C3, and 0 multiplied by C4. So this is C. When you multiply a vector by a matrix, you are taking a linear combination of the columns of that matrix. So how do we feed a word or multiple words into the vector? You multiply each word or multiple words are input into the neural network as a hot or a sparse vector, depending, are you using skipogram or are you using continuous back of words? And this is actually just a weight matrix. This is each column here represents weights, W1 to Wn. And as you do back propagation, you will figure out these weights. And once you figure out these weights, you figure it out how to represent a word as a vector. So each column here represents the vector of a separate word. So basically, when you are inputting the hot vector, can you, Ali, tell me, we are selecting a vector. If you are inputting two ones, that means you are selecting two vectors and you are summing them together. This is a simplification of how these algorithms work. And again, it's just a loss function. Once we minimize our loss function, we figure out the model. And in that case, we figured out the weights in this nice, beautiful matrix, colorful matrix. And this matrix is just the weights, and each column, the weights of each column represents our word as a vector. And I hope that you enjoyed the presentation. And if you have any questions, we can cover that.